Awesome. So first of all, Jesse, thank you for having me. The Hacker House has been absolutely amazing this last week, and I am super excited to walk everybody through Gnark Plonk and how to implement an end-to-end prover in the GPU. Okay, so quick overview. So what's the problem we're trying to solve? So running large circuits on the CPU, it's really slow, and it's really expensive. So our solution to this is implementing a Plonk prover on the GPU using a GPU-specific library developed by Inganyama called Icicle. For this presentation, we're going to really go in 3 steps. So first, we're going to give you a quick background on Inganyama, Icicle, and why using the GPU makes sense. Then we'll do a quick overview of the actual Plonk protocol. We'll go through what it looks like at a high level. We'll walk everybody through like the actual rounds that happen in the protocol, and then we'll really highlight what the bottlenecks are. And then finally, we'll do an actual walkthrough of the code and see how we accelerate the Plonk prover on the GPU using our Go Icicle bindings. So we'll talk about a little bit about how we set up the device memory, how we set up the device itself, and then how we actually run the entities and the MSMs on device. So I think before we start, I think when most people think of like ZK hardware acceleration, we kind of have this image of like some dark factory somewhere with like a bunch of mathematicians like playing with chips trying to like figure some weird thing out. And it feels like very intimidating. It definitely felt intimidating to me when I got started. But I think hopefully with this presentation, it can really show you really how accessible 5 and 10x speedups are on actually like cutting edge proof systems and how we can really achieve that from a pretty high level. So what is Inganyama? We are a ZK startup based out of Israel. We are focused on ZK hardware acceleration. And really like our goal is to identify like what are the key primitives that are used across different ZK proof systems. What are the bottlenecks that are presented by those primitives, and how do we algorithmically accelerate those bottlenecks? So right now, our real focus is on supporting the number theoretic transform, the NTT, multi-scalar multiplication, and then ZK-friendly hash functions. What is Icicle? Icicle is our library for ZK acceleration using CUDA-enabled GPUs. So CUDA programming, if you're not familiar with it, is essentially basically C++ with a few additions from NVIDIA, and it's relatively low level. So Icicle exposes both like the low level CUDA functionality, and then we have added wrappers on top. So what's inside Icicle? So we have a high level Rust API, a Golang API, and then you can also access the CUDA API directly. The design is to be very high level to enable protocol developers to directly unlock the power of the CPU without having to drop down to the CUDA level. What we currently support is vectorized field and group arithmetic, polynomial arithmetic, Poseidon hash, different curves, and then more complex structures such as the EC MTT, batch MSM, and Merkle trays. So why Icicle? Like the GPU programs are like a little intimidating for everybody, right? So it's like the goal is to unlock that power and give it to developers without like forcing them to spend hundreds of hours going through the NVIDIA documentation itself and really understanding the CUDA, but still give you all the power of the GPU. And like the problem really solves is, so all the modern Snark frameworks people are probably familiar with, such as Rapid Snark, Halo 2, Gnark, ArcWork, right now they only support CPU. So if you're running any prover with these frameworks, you're going to be running it on the CPU. So the real goal of Icicle is to fit in with these frameworks and enable specific functions to be ran on the GPU. So why GPUs? High-level access, low-level performance, relatively simple for developers to use, parallel processing, increased memory bandwidth, and then they're extremely competitive with FPGAs in terms of power and performance and price, and also a lot faster to develop for. The way I really think about GPUs is like we think about a lot of like the big breakthroughs in computers over the last 30 years. So, you think of like the old Super Nintendo, and it's kind of like flat, one dimension or two dimensional, and like really not alive. And then you start to really like program for the GPU in the mid 90s, and that starts to be developed. And all of a sudden you have Quake, you have Unreal Engine, you unlock like this whole new world for video games. And then in the mid 2000s, the same thing is happening when we start to run a lot more machine learning on the GPUs, and we unlock kind of this whole new world of machine learning. And right now, the same thing is happening with ZK. We're like in the very early stages of that. But that same process we've seen happen over the last 30 years is slowly being incorporated with ZK. Okay, so let's dive in and just do introduction to Plonk, kind of explain what's happening, and start thinking about like where some of the bottlenecks are actually occurring in the protocol itself. So the first thing we're going to have is our circuit. Then we're going to generate our witness. We're going to run a Lagrange interpolation, and then we're going to commit to trace. So this commit to trace is our first MSM commitment. From there, we're going to write to our transcript, which is evaluate H poly, where we calculate our quotient polynomial. We're going to run another KZG commit, generate the proof, and then run a batch KZG aggregate circuit, which is going to be another MSM, and then we will finally have our proof. So when we think about like the bottlenecks that occur in ZK, there's really two main bottlenecks. The first is the commitment bottleneck, which is the multiscalar multiplication. And that's really a computational bottleneck. And these algorithms are very parallelizable on the GPU. And then our second bottleneck is the constraint evaluation bottlenecks, which are the FFTs. These are both computationally and memory intensive and require a little bit more optimization to get just right. So I guess just to kind of understand how much time each of these things are taking. So for our benchmarks on the CPU, for a circuit size of like 2 to 24, this commit to trace, that's taking about, the total time is about 86 seconds. This commit to trace is taking about 10 seconds. This evaluate H poly, the quotient polynomial, is taking 47 seconds. So that's just huge. And then the follow-on KZG commits are each taking about 10 seconds. For about like 75 seconds of the 86 total seconds proof time can be optimized on the GPU, and the remainder are kind of like, that just is what it is. So around 80% of the total proof generation time can be accelerated on the GPU, and we're going to walk through and see how that is. Before we actually dive into the actual code, we're going to walk through the different rounds of the Plonk prover and really see where these NTTs and MSMs happen. So this is round one of the Plonk prover. So the first thing that happens is we generate blinding scalars. We have to compute our wire polynomials, which requires a Lagrange interpolation. That's an NTT. And then we have to compute the commitment to those polynomials with our blinding polynomials as well. So that's round one. Round two, we're going to do the exact same thing for our permutation polynomial zeta. And then round three, like this is like the big, like this is where all the action happens in Plonk. So the first thing is we compute the quotient polynomial, which is a bunch of NTTs over all our witness polynomials and a bunch of vector multiplication. And then finally, at the end of this, we're going to compute a commitment to the final quotient polynomial. Round four, we take a break. There's no NTT, no MSM, nothing to accelerate. And then in round five, we compute our opening challenge, compute the linearization polynomial, which requires the NTT and MSM, and then finally a batch open MSM at the end. So that should give you a really high level overview of like going through the paper, the actual Plonk paper, like, okay, this is where these primitives are happening. This is what we can accelerate. And this is very useful prior to like diving into the code, because it's a really helpful framing to understand, like, okay, these are the exact primitives we can accelerate. These are where the primitives happen. And then the next step is to actually like walk through how we actually do it in the code. Okay, deep breath. Everybody okay? Like no more math. Let's write some code. So what is Gnark Plonk? So Gnark is a ZK library written by consensus in Go. They have implemented Gras16. They've implemented Plonk. I believe they have potentially Hyperplonk implemented on a number of different curves. So this is what we're actually going to be accelerating. So we've identified the bottlenecks. That's the first step. Next step is we send data from the CPU to the GPU, and then we run our compute on the GPU. Just overview of this part of the presentation. We're going to give a high-level overview of the device architecture, how we set up the device, and then how we actually run the MSM and NTT on the device. Okay, so device host architecture right here. So Gnark is what we're actually accelerating. This is where the prover is. Go Icicle is our interface between the Gnark prover and the actual the CUDA code that we're going to run on the GPU. So basically everything in yellow, that's all happening on the host, on the CPU, and then on device, that's what's happening on the GPU. So Go Icicle is really what we use to send our data types, our ZK data types from the Gnark library over to the actual to CUDA. We're going to be able to convert those data types to something that makes sense in CUDA, in the CUDA world, and then we're going to be able to run that on the GPU. Okay, so our memory architecture. So here we have the host and the GPU, or the host and device. The PCIe is just the bus, the memory bus between the host memory and the GPU memory. At a really high level, so we have our CPU memory. The first thing we're going to do, we're going to send it to the device, and that's going to get stored in the global memory on the device. From there, we are going to instantiate a number of kernels. Each kernel holds different blocks, which we allocate, and the blocks contain shared memory. So we're going CPU memory, global memory, shared memory on the blocks. Once our shared memory is on the blocks, each block is going to be able to run separate threads, and the threads are local memory. So that's where like the really low level operations are happening. So we're going to run all the compute in local memory. Once our compute is done, we're going to follow that same process and step it back to the CPU. So we're going to go to shared memory, global memory, and then finally to CPU memory. So this is really important because we've talked about the bottlenecks we're solving. So the bottlenecks we're solving is the NTT and the MSM. But if we're not really careful, we're going to introduce a new bottleneck. And that new bottleneck is the read and write between the CPU and the GPU. So what we don't want to have happen is introduce an even bigger bottleneck by trying to solve the original two bottlenecks. So the way we really think about this is, as we're designing the GPU prover, we want to really minimize the amount of read-write operations between the CPU and the GPU. So we want to get everything from the CPU onto the GPU as soon as possible, run as much computation as we possibly can on the GPU, and then at the very end, we're going to want to write it back to the actual CPU. Okay, so getting started, the first steps we're going to do, Bone and I, we did this today many times as we were working together. So first thing you need, if you're going to run this on your computer, you need CUDA Toolkit, CMake, and GCC, and a NVIDIA GPU. So kind of like the first thing you're going to run into is like you're either going to have to SSH into a remote server, or you're going to have the NVIDIA GPU on your local machine. You're going to clone and build our Icicle library. This is going to build like the static libraries. You're going to need the static C++ libraries you're going to need to call. run the Go tests, and then import Icicle into your project and use our Go bindings to actually call the functions we need. Okay, the Gnark Plonk prover overview. So this is in just the prove.go file in the Gnark Plonk prover. So the entry function is this function is prove. And it takes as an input our R1CS, our proving key, and our full witness. And those are all generated on the CPU. This, like, all that is happening before we get to the GPU. And the thing we're really going to think about here is the proving key. And because the proving key is going to have a lot of information that we want to get to the device as soon as possible. So once we have the proving key, we're going to call setup device pointers to start actually setting up all the pointers we need prior to running any computation, any of the actual the Plonk functions. And then on the far right, those are all the functions, like those are the top level functions for the Plonk prover. They don't like map one-to-one to the paper, but it's like it's close enough that you can kind of follow along. Okay, so device setup. This is probably like the most important part because this gets everything we need, or like 50% of what we need, over to the GPU. So some of the data we want is we want our twiddles inverse, our KZG G1 and KZG G1 Lagrange fields, our cosets and coset inverse. I think it's really important, like these are being, when they're written to the GPU, we're allocating actual memory in the GPU. So we're going to need to ensure like what we're telling the GPU how much memory to actually allocate when it's getting this data. And then this is going to return unsafe pointer to the CUDA memory location. And we're going to be able to use that pointer throughout our prover to call the CUDA functions we actually need. So here on the right side, you can see we're getting the size we need. We're multiplying it by the size in bytes for the field elements using the consensus FR bytes library. We're creating a channel with an unsafe pointer. And this channel is basically going to, like when the Go function is done, like that's what the output is written to, and then we're going to be able to copy that to what we need to actually like run the full the prover. And then after that, all we do is we call Go Icicle copy to device. We copy our coset table, our size bytes, and then the channel. And once that's done, it's going to be written to wherever we want to store it, and we're going to have that that pointer on device, like ready to do any computation we want. Okay, so we get to our first MSM. So this is commit to poly and blinding. Just for reference, this is happening during the first round of the Plonk prover. We've generated our blinding polynomials. We've generated our witness polynomials, and now we need to actually make a commitment to those polynomials. So we have basically half of what we need on device. So we have the G1 field, but we don't have the coefficients on device, right? Because we've like generated those later in the prover. So what we need to make happen is we need to call KZG on device commit, which is going to take our polynomial coefficients. It's going to take our field, and it's going to generate the commitment. And then we're going to do the same thing for our blinding polynomials. So let's dive in. Let's look at this on-device commit function. So on-device commit is a little bit long, and the reason it's a little long is because we still need to write those polynomials to the CUDA memory. So we're taking the length of the polynomial, multiplying it by bytes to get enough size. We're setting up our channels. We're copying the polynomial to device. And then here on the right side, once it's on device, we're calculating the actual MSM on device, which is that device value, the G1, the size, and that is the MSM on device. So that's fully ran on device. And there you have it. We have our first MSM in the books, ran on the GPU in 50 lines of code. So we're making progress. We're going to run this for all our witness polynomials, and we're going to basically follow the same process every time we have to run an MSM. So I think this is a good point to pause for just a second. There's two ways of implementing a prover on the GPU. So you can do drop-in or you can do end-to-end. So drop-in is basically means we're replacing the MSM functions, and if the polynomial, if it's not on device yet, we're writing this device, we're running it, and we're writing it back. And that's like not optimal. The optimal way to do this is to have everything be on device throughout the entire proof and run everything we need on the device. And that's a little bit more complex. It's going to take a little bit more time and is a little bit outside of this presentation. But that's kind of like the difference. And like that's where we start to get like the real 10, 20x unlocks in time when we're running everything on GPU. Okay, so NTT. There's a bunch of NTTs that happen in Plonk, but probably like the 47 seconds of NTTs are what we really want to accelerate, right? So these NTTs happen when we are calculating the quotient polynomial. These are like the 47 seconds of NTTs that are happening in the prover. So within Gnark Plonk, calculate quotient polynomial is probably 400 lines of code. It's a very complex function. It has a bunch of internal functions as well. And we're just going to pull out one of those internal functions, which is called batch apply. So if we're going to calculate the quotient polynomial, basically we follow 4 steps at a very, very high level. The first thing we do is we calculate the permutation coefficient rho by dividing our large domain by our small domain. And then for each element in rho, we convert all our witness polynomials to Lagrange form. We multiply by our scaling factors. We convert back to canonical form. And then we evaluate that new polynomial on the constraints. And then finally, at the end, we'll get our quotient polynomial h. So here with batch apply, we are basically running these NTTs for each of our witness polynomials. And we're following like a very similar sequence to what we did with the MSM. We need the polynomial size. We're getting our scaling vectors, which are the twiddles and the inverse. As you know, like those are already on device. And then we're going to set up a channel to run the actual computation. We're going to run compute INTT NTT on device, which takes a pointer to our polynomial. It takes another device pointer, which is where the output is going to be written, and those are unsafe pointers. So the first thing we're going to do is we're going to run the INTT on device to go to canonical form. Takes the device pointer, the twiddles inverse, and our size in bytes, and it outputs a unsafe pointer a INTT d underscore d. Next thing we're going to do is we're going to multiply that by our scalars. And then finally, we're going to run the NTT on the device. And this is like the pause point, right? So here, oops. Uh-oh. Okay, it's okay, it's okay, it's okay. We're pretty close to done, so I think it has at least 5 minutes of memory left. So at the end, we're going to write everything we calculated back to the CPU, and then we're going to run our constraint evaluations on the CPU. We could do this all on the GPU. For this implementation, though, we're writing it back to the CPU, and that is how you run the entities on device, and that is how you start to really accelerate the Plonk prover. So here are our benchmarks. On the far right side, those are our CPU baseline benchmarks for the circuit size of 2 to 24, 86 seconds. You can see the MSM, like the first commitment MSMs, are taking about 5.5 seconds on the CPU, and that's dropping to about 1 second total on the GPU, so about 5x. One thing to note here, in Gnark, a lot of what they do to accelerate on the CPU is they run asynchronous processes. So they run a bunch of threads on the CPU. That doesn't quite translate over to the GPU because it's very difficult. Like, you don't want to start a bunch of CPU threads and send all of those separate threads to the device, because the threads are kind of happening at a different level where the CPU threads are happening at the OS runtime, and then GPU's like at a lower level. So like you have to run the GPU calculations in sequence, or stuff is just going to start getting like mixed up with the pointers. So that's just one thing to note here, that these are ran sequentially. And then we go down to our compute quotient polynomial, 43 seconds on the CPU. Doing just the drop-in replacement, we cut off about 20 seconds, get it down to 27 seconds. And that 27 seconds, like that's not, like the slowdown there isn't happening because the NTTs aren't fast. We're just adding more time because we're writing back to the CPU here. But if we run that all on the GPU, that goes down to 7 seconds. So that's like a huge speed up. And you can see each of the NTTs here is taking about like between 1 and 4 seconds and dropping a lot. Then you can see our commitments here, also very fast, and then a total time. So end to end is about 30 seconds. Drop in is about 48 seconds, and that's an improvement on the 86 seconds on the CPU. We use the Succinct Labs circuits for the benchmark. So getting started is easy. ZK hardware acceleration is super fun.